let's start talking about these important reactions that carbonyls, aldehydes, and ketones undergo. Nucleophilic addition. That's where a nucleophile attacks and remains as part of the molecule. So the carbonyl carbon is electrophilic, right? Let's draw carbonyl, C double bond O. There is an important resonance structure. It's I guess a minor structure, but still plays an important role in the properties of the compound. So if one pair of those double bond electrons go up on the oxygen, I end up with essentially like an alkoxide, but with a carbocation next to it, C+. That just means that a carbonyl compound has a significant partial positive charge on the carbon, partial negative charge on the oxygen. So that's why this carbonyl carbon is electrophilic due to resonance withdrawing as well as inductive withdrawing. Oxygen is more electronegative anyway than carbon, so it pulls electron density from that carbon just through the sigma bond. So a variety of nucleophiles can attack a carbonyl, right? Negatively charged nucleophiles like hydroxide or hydride or a carbanion, an alkoxide, a cyanide. Those are common nucleophiles that can attack. Also neutral nucleophiles can attack under certain circumstances that we'll talk about. But what happens, the nucleophile adds to the electrophilic carbon. It pushes the electron pair from the C double bond O up onto the oxygen, making an alkoxide intermediate. The nucleophile adds perpendicular to the plane of the carbonyl, right, of those two R groups, about 75 degrees from parallel. So the carbonyl carbon rehybridizes, so there's a change in hybridization. It was originally sp2. In the alkoxide intermediate, it is sp3. One common thing that's done is then protonation. So if our second step is acid, we'll protonate the alkoxide, making an alcohol. Okay, so that's a very common reaction that carbonyl compounds will undergo, like the Grignard reaction, where we have a C- that's attacking the carbonyl carbon, making an alkoxide. The second step is protonation, and we get the alcohol as a product. That's essentially what happened here, right? Negative nucleophile attacks, we get an O- that's protonated. Something else that can happen is if I have a neutral nucleophile or a nucleophile that also has H's attached to it, what can happen is rather than protonating the alkoxide, we can do a proton transfer where one of the H's from the nucleophile goes to the alcohol, and then we can even remove a further H along with removal of water in order to make a double bond from the nucleophile. This is very common with nitrogen, as we'll see. Not so common with oxygen nucleophiles. So aldehydes and ketones have different reactivities. Aldehydes are usually more reactive for both steric and electronic reasons. Sterically, the carbonyl carbon of an aldehyde is more accessible than that of a ketone. It has one fewer R group there, so a nucleophile is more able to approach it and attack. Electronically, that's a demonstration down here, the ketone's carbon is less electrophilic because it has two R groups donating electron density into it. So take a look. If we imagine we had a primary carbocation, that would be less stable, right? Just like we have an aldehyde with just one R group, that's less stable because there's more of a partial positive charge there. Whereas the ketone is stabilized by the two R groups. Right? The secondary carbocation similarly has two R groups, so it's a little more stable. One way of thinking of this, because the aldehyde is less stable, right? It starts out higher up on the reaction energy diagram than a ketone would, where if we're doing a reaction, say something like that, where we do a nucleophilic addition to it. The ketone would have a higher activation energy, right? Even though the transition state itself isn't as high, here is activation energy, right? Oops, let's call it what it is in this book, delta G double dagger. So aldehydes will be more reactive because there's less of an uphill climb to get to their transition state. The activation energy has a lot to do with the steric hindrance. Right? If I have a hindered transition state, that's going to be up higher in energy. So those factors make aldehydes more reactive, and we'll take advantage of that in some of our reactions in a little bit. Another thing that can influence stability is if I have a carbonyl attached to a benzene ring, for instance, the benzene ring can donate electron density by resonance towards the carbonyl. So it distributes the plus charge at the ortho and para positions in a carbonyl compound like that. So that means there's less positive charge on that carbon there. So formaldehyde here in this electrostatic potential map is very blue. Formaldehyde has more partial positive there. Benzaldehyde has less partial positive because the pi electrons in the ring have donated towards it and have distributed the plus charge throughout the ring, essentially. So conjugated, let's just make a little rule here, conjugated carbonyls are less electrophilic themselves. There's something different they can do, but we'll talk about that at the end of the chapter.